Hello friends, this is a video about the alternating series test. This is determining whether or not a series converges, and it has to be of a certain form. As always, it's easier to show you than to describe it. So let me pull up something on my iPad here. And the Mac will try to get me to use iTunes again. Okay, so this that I've written out here, I went ahead and wrote the whole thing ahead of time because of the fact that there's a little bit of drawing and stuff, so this is meant to save some time. So if we're looking here, our alternating series is going to be a series that has something in it that's on the nature of -1 to the n. It could be, and I'm going to turn off notifications, it could be that it has -1 to the n plus 1 or something different. Notice if it has -1 to the 2n, that would always be +1. If it has -1 to the 2n plus 1, that would always be -1. But if it has -1 to the n, or -1 to the n plus 1, or -1 to the n minus 1, those are all essentially just the same thing, just a little different, okay? So with your alternating series, you need to be talking about the an portion of it, the part that's not the -1 to the n, needs to be something that's always positive. And then we need to have something that's decreasing or is eventually decreasing, just like eventually positive is okay as well. And we need to have the limit as n goes to infinity of a sub n turning out to be 0. If we have those three things, that series converges. And that should feel like it's cheating because it feels like we just used the nth term test to prove convergence. And that's not what we did, because we had the nth term test just isn't enough. When we have an alternating series, that means it needs to alternate not just randomly back and forth from -1 to +1, but each successive term goes back and forth. So if we looked at the positive terms and said, this is A1, this is A2, this is A3, this is A4, this is A5, and so forth. And I cannot magnify that on the screen, annoying. But if we were doing that, because of the fact that we might have the first term being positive and then the next term being negative, that means that we would have some area above the axis for the first term, but the second term is some area below, and somehow that got stretched. And so when you add that A1 and that A2 together, the part that's negative gets canceled off and you only get a little bit there, okay? And then between the A3 and the A4, because the A4 is negative, then you cancel off a little bit and you don't get all of A3. So the thing that's going on with this is not just that you have terms going to 0, but that you have terms going to 0 and you're looking at the difference between the consecutive terms, okay? So we have a little bit of language stuff to say about that as well. If the summation of the a sub n's converges without the alternating part, if just it converges without that, then we say that the series converges absolutely. And if the series converges absolutely, then that means that the alternating series converges, but it also means a little bit more. If, on the other hand, we have this condition of having an alternating series that converges, but the positive series that goes with it diverges, we say that it converges conditionally. So a quick example of that would be if we looked at minus 1 to the n times 1 over n. And you know that summation 1 to infinity 1 over n, you know that that diverges. Okay? But that 1 over n is positive, and since 1 over n is always more than 1 over n plus 1, you could also do that using a derivative, okay? Then you have positive decreasing, and the limit as n goes to infinity of 1 over n equals 0. So summation n equals 1 to infinity minus 1 to the n, 1 over n, converges conditionally. Okay. So that is a bit of language that's going to come up with these occasionally, that you have something that converges conditionally or converges absolutely. And iTunes is coming up again. So, all right. So I want to try to look at a couple of more examples, three more examples there real quick that illustrate this kind of thing. Okay, so here's another alternating series, and what we're looking at is a summation n equals 1 to infinity minus 1 to the n over the square root of n plus 1. Okay, so you know that if you wrote that as a function f of x, that it would be just quantity x plus 1 to the minus 1/2 power. That's always going to be positive because the values that you'd be putting in for the n or the x are always going to be positive. Okay, and further, it's a square root. Then if you took the derivative of it here, you would get a something to the minus 3/2 power, so essentially a square root. So that part will be positive, but times the minus 1/2, so it's negative, and that tells you it's decreasing. And so once you take that limit and see that it goes to 0, you know that the series converges, all right? And that is converging using the alternating series test. But if you're asked in the instructions not to determine whether it converges or diverges, but determine the convergence, then we're probably asking you to decide, does it converge conditionally or absolutely? So then you go in and take a look at this series, just throwing off the minus 1 to the n. And so you know that that's like 1 over the square root of n, which is 1 over n to the 1/2 power. And that's a p series, and p series always diverge if the p is 1 or less. So since that's a divergent p series, we can talk about doing a comparison. And remember the limit comparison thing we did the other day? Since it's not exactly a p series, we have to go ahead and say, okay, let's divide those two things. And when we divide them, we can combine the square roots and we can get a limit of 1. That limit is neither 0 nor infinity, so we don't have to pull any fancy tricks with it. We can just go ahead and say that this series here diverges. And so that means that the original series that we were interested in, it converges, but its absolute value does not converge. So it converges conditionally, not absolutely. Okay? So that's a quick example to look at on that sort of thing. And so a lot of the things that you tried the nth term test on before and it was inconclusive, now you can actually go ahead and use them. Okay, so another one along those directions. I mean, summation 1 over n was something that diverged but passed the nth term test. 1 over the square root of n, it diverged, the summation diverged, but it passed the nth term test. So anything where you've got that limits turning out to be 0 is a candidate to try on this. And so let's take a look here at a summation that has a logarithm in it, because logarithms go to infinity much slower than any polynomial does. Since we have a summation from 2 to infinity, then that means that the logarithm, you're taking a log of something bigger than 1, so it's going to be positive. And when you take the derivative of 1 over the log, then you will end up with a negative 1 over x times log quantity squared. And that is going to be something that's always negative, so then you've got it being decreasing. So once you take a limit of 1 over log n and get 0, that tells you that the summation with the negative 1 to the n over log n is going to converge. But we're interested in seeing how it converges. So we can take a look here, and we know that a log of n is always going to be less than the value of n itself. Okay? And so that means that 1 over that logarithm will be more than 1 over n, because when you take reciprocals, it will flip the inequality as long as they were both positive. Okay. Anyway, so you can then have that set up to do something with the direct comparison test, because we know that the summation 1 over n diverges because it's a p-series is p equal 1. And that says that the summation 1 over log n diverges. I forgot to write by the direct comparison test. Okay. So since the original series, the alternating series converged, but its absolute value, when you threw off the -1 to the n, didn't converge, that's conditional convergence. Okay. So when you have to show conditional convergence, you always have to go through all of that kind of a mess in doing it there. So, all right. I always like to try to do at least one that's really kind of messy here. So the next one that I've got is involving something that you'll run into where you have to think about sines and cosines, okay? One thing you will frequently see is that instead of writing -1 to the n, sometimes they'll write cosine of quantity in pi. And you're like, how do I know what that does? You plug in some n values. When n equals 1, cosine of n pi, try it again. Yeah. Cosine of n pi means cosine of 1 pi. Cosine of pi is -1. Cosine of 2 pi is +1. Cosine of 3 pi is -1. Cosine of 4 pi is +1. Get the pattern? Whenever it's odd, you get a negative. Whenever it's even, you get a positive. So that's one that you'll see come up fairly often. And in particular, if you're doing anything in physics, you're going to see something about Fourier series eventually, and that will show up in your calculations. Okay. So here is one that is a little bit convoluted. okay? So this one, we have the summation n equals 1 to infinity, and it says sine of n pi over 4. If it had said n pi over 2, it would have looked a little bit more like that cosine thing. But n pi over 4, we just have to think about our unit circle and plug in and get it. So the cosine of 1 pi over 4 is 1 over root 2. If you like to write root 2 over 2, write root 2 over 2, I don't care, all right? Then the sine of 2 pi over 4, well, that's the cosine of pi over 2. That is 1. And then for 3 pi over 4, you get positive 1 over root 2. For 4 pi over 4, you get 0. And then for 5 pi over 4, you get negative 1 over root 2. For 6 pi over 4, you get negative 1. For 7 pi over 4, you get negative 1 over root 2. For 8 pi over 4, you get 0. And then we start repeating, okay? Which you're like, what's going on here, okay? And I made a copying error as I did this. I forgot to put my squares in here. I should have had squares. Okay, fixed. So here is a super nice thing. You know that that looked a lot like 1 over n squared, right? Because it had stuff in the numerator, you know, that was between -1 and 1. As a matter of fact, all signs are always between -1 and 1. So if we take this absolute value of that thing, we know that the sine of n pi over 4 divided by n squared would be between -1 over n squared and +1 over n squared. So in fact, taking the absolute value, it'll be less than 1 over n squared. And we know summation 1 over n squared converges by p series. So that tells us that the summation of the absolute value converges by the direct comparison test. So once you know that the summation of the absolute value converges, there's no need to check the alternating series. You immediately know it converges absolutely. Boom, you're done. I was thinking that was going to be more complicated than it actually was, but it was mostly the write out stuff, okay? So alternating series, remember that when you establish whether the positive part converges or diverges, you have to make the citation, direct comparison test, limit comparison test, integral test, some of those things like that, okay? Otherwise, it's relatively straightforward, more so maybe than some of the previous tests. So, all right, see you next time.